So the idea now is to talk about how can I find the matrix that transform a matrix into its Jordan form. I mean, if I have a matrix, here it's A, and I have a Jordan canonical form of this matrix, let's call it J, how can I find the invertible matrix P such that P minus 1, the inverse of P, times AP equals J? You know, like we are doing in diagonalization, but now for a Jordan form. So when it's diagonalized matrix, it's very simple because it's the same as diagonalization. We'll go throughout this, but we'll go throughout also a matrix that is not diagonalizable. So the Jordan form, or the matrix that will transfer the matrix A to Jordan form, will be quite different. You remember that if I can diagonalize a matrix A, the matrix P is just the eigenvectors corresponding to the eigenvalues as columns of the matrix. This is how we construct P when A is diagonalizable. But now, if A is not diagonalizable, we have a problem because we don't have enough eigenvectors to construct the P matrix. This is why A is not diagonalizable. The algebraic multiplicity is not equal the geometric multiplicity of each eigenvalue. This is the problem. So we don't have, when A is not diagonal, we don't have enough eigenvectors to construct a P matrix. So what will we do? Let's start. So here we want to find P that satisfies this for a matrix A and Jordan for J. What we should do? We should, as usual, like in diagonalization, we'll go and find the eigenvalues of A, doing like this, A minus lambda I, determinanta, get the determinant, and equal to 0, you will find the characteristic polynomial, and from that, the roots of the characteristic polynomial will give you the eigenvalues. And by computing the algebraic multiplicity and geometric multiplicity, like from the characteristic polynomial or from the kernel, you know them, you can know how many blocks you have and what is the biggest size, so you know the number of Jordan blocks for lambda. The number of blocks is the geometric multiplicity, and the sum of sizes of the block equals the algebraic multiplicity. Anyway, you can construct the Jordan form by this. Now, if the matrix is not diagonalizable, you need to do this. After you find the eigenvectors, you will find what is called generalized eigenvectors. You find the eigenvector, which is this one. You solve this in order to find the eigenvector for the eigenvalue lambda, right? This is totally normal. Now, you will find a chain of generalized eigenvectors by doing this, taking A minus lambda I times V2 equals V1 and not 0. This is the next eigenvector. Now the next eigenvector, V3 equals V2, and so on and so forth. We are constructing chain of eigenvectors. And from this chain of eigenvectors, we will construct a P matrix. Let's look on an example. For example, this one. No, let's go for another one. Let's start with an example that is totally simple. This is diagonalizable, so this is the matrix. I want to find the Jordan form. You are doing the eigenvalues. You are seeing the characteristic polynomial. You have distinct eigenvalues, 3 eigenvalues, each one with algebraic multiplicity of 1. So geometric multiplicity was also 1. So it's diagonalizable, and this is the Jordan form. So it's quite easy to find the P because it's just the eigenvectors as columns. You see, I'm finding the eigenvectors for each eigenvalue. This is the first eigenvector, this is the second. I'm just plugging in the eigenvalues, and this is the third eigenvectors. So P is just putting the eigenvector that I found as column of P, and I get the P that I need. Now, if A is not diagonalizable, like in this case, so I find eigenvalues, for example, lambda equals 2, multiplicity of 2, but the geometric multiplicity will be of 1. So I have only one eigenvector, but I have two eigenvalues. But I have multiplicity of 2 for algebraic multiplicity. But I need two eigenvectors because this is a matrix of size 2. What will I do? I'll take v2, plug it in to this, and say it equals v1, and get another vector. This is the second eigenvector, and here it is, putting the eigenvectors as column and getting the P matrix. Let's do another example. So you can see that right over here. We have all eigenvalues are 3. This is R5. This is a upper triangular matrix. The eigenvalues are on the diagonal. So algebraic multiplicity and geometric, you can see over here, it's not diagonalizable. So I find the eigenvectors, I find just one of them. Now let's do the chain. V2, plugging into here, I found the eigenvector by doing this, taking a minus my eigenvalue I, v equals 0. Now I will do it v2 equals v1, v3 equals v2, and get two more eigenvectors that I need in order to construct the matrix P. And here are the eigenvectors. Okay, this is the Jordan form. Okay, now if I have a matrix A, with two eigenvalues, each of algebraic multiplicity of 2 and geometric multiplicity of 1. How then do I do that? Create a concrete example. Now let's see when I have two eigenvalues that both of them has algebraic multiplicity that is higher than the geometric. So what will I do? You see that for the eigenvalue 1, I get the eigenvector, but I need to do a chain to find the second one. And for the second eigenvalue, I'm doing the same. Find the eigenvector and finding another one, because I need the number of algebraic multiplicity, number of eigenvectors. And those I take those eigenvectors, put it in a matrix as a columns, and this is my P, and this is how I found the P minus 1 AP equals J. So you also see in a case where I have more than one eigenvalue, where its algebraic multiplicity doesn't equal the geometric multiplicity. So I wish that it's quite clear to now understand, even if the matrix A is not diagonalizable. If it's diagonalizable, it's very easy. It's like diagonalization. You find the eigenvectors, put them in the columns, and this is P. But if A is not diagonalizable, you will need to do the chain of generalized eigenvectors as we saw, and this is how we find the P matrix to get from A to the Jordan form. Okay, so this is it. Thank you very much. If there are any mistakes or correction, please tell me. Thank you all, and that's it.